let's start looking a little bit at scientific thought and matter based out of chapter 1. Okay? So, how many people read the book, did the reading, and saw a strawberry pie? You saw a strawberry pie in there? Oh, okay, good. I was like, I didn't think there was one. Okay. So sometimes you'll see figures from the textbook, sometimes you won't. This is one where I wanted to add it. Why science? Right? So what do you see there?
Strawberry pie.
Strawberry pie. If you're a pessimist and optimist, everybody know what those terms are? Mm-hmm. Okay. If you're a pessimist, what do you see?
Strawberry pie I can't eat.
Strawberry pie I can't eat. Pessimist sees that. Why are they saying they can't eat it? That would be a realist, different category.
I'm on a diet.
Okay?
I don't like strawberries.
Okay. Diet. Seriously?
I do, but
Oh, okay, just checking. Well, that just seems so foreign to me. Okay? Okay, don't like strawberries.
Allergic to strawberries?
Yeah, that could be a reason you don't like strawberries. Okay?
Don't
Okay.
like strawberries?
Too much sugar. Okay, gluten-free. Or gluten intolerance. Okay, whatever you want to do. Okay, what would an optimist see? Strawberry pie. Awesome, fantastic. This is tasty. I'm going to enjoy life. This is phenomenal. What does a scientist see? Everyone's like, I don't want to be wrong. Could look at the composition of the pie. Okay? The things that made up the pie. Why? Why science? Why does a scientist care what makes up the pie?
Because that's what it needs to, like, to make a pie a pie.
Okay, so for the sheer knowledge of saying a pie exists, I just want to be able to explain to other people that this is a pie, so I have to tell them what those pieces are. All right, that's pretty noble. I would argue that's not true, but any other ideas?
Curiosity.
Maybe he wants to
Curiosity.
put it in his body.
What he's putting in the pie, why?
No, what he's putting in his body.
Or what he's putting in his body. Okay? Addressing how that's going to affect the human that eats it. Okay? That could go back to the pessimist kind of angle. My argument for what a scientist sees here is wants to know all of that information. I want to know what goes into it. And not for some noble purpose of being able to tell everybody this is how you make a pie. Because they see that pie and they say, I can make it better. Okay? Scientists, at their most fundamental level, are egotistical. Okay? They see that and they say, I can do better than that. So, yes, those are strawberries, but those strawberries were shipped across the oceans, okay, lost some of their good value or their nutritional value, if I want to look at what's going into the body, or lost some of their sugar content or didn't develop their sugar content so they don't taste as good. Okay? So instead of sourcing the strawberries from thousands of miles away, I'm going to source them from much closer to home. Personally, I would say California in the middle of summer, because that's when strawberries are in season and they are better. Okay? Roster list still needs to go forward. Okay? Why do they want to do that? Okay? Have you ever think about scientists? Anybody know a scientist? Yeah. What scientist have you heard of?
Oh, like in person or
No, just heard of.
Stephen Hawking?
Stephen Hawking.
So you said about making it better, reminded me of Walter from Breaking Bad.
Okay. Which is arguably a scientist. What did he do? He saw the drug industry and said, I can make that better. Right? Just because what he's doing is illegal doesn't make it not a science.
He's a chemistry teacher.
Right? We're focused on that making it better. And a lot of it is egotistical. And if we think back to what we classically associate with science, we think of scientists as these big, brilliant, genius people. Okay? Why do we think of them as big, brilliant, genius people? When they went through and made their discovery, what did they do? They published it. Said, hey, look at me. I did something cool. Okay? And then forever thereafter, we remember that name because they did something cool. They did honestly do something cool, and they do deserve some credit. Don't get me wrong. Okay? But that's why we become scientists. Okay? Is we're dealing with that kind of egomaniacal, I want to make something better. And it can be as grand as just, I just want to make a better strawberry pie. Okay? If you've ever been in the kitchen making a strawberry pie and you taste it and go, oh, that was crap. Okay? You could just give up. Okay? And this is one of the things that scientists tend not to do because they're egomaniacal. I know I can do better. Okay? And so they don't give up. They go back and they make another pie. And they make some adjustment to that pie. Ideally, they take notes about the adjustments they made. Okay? All of that work is what a scientist is doing. No scientist, very few scientists, I should be careful with that, very few scientists sat down and went, perfect strawberry pie. Of course, they didn't do a pie, but perfect anti-cancer drug. Cures all world's ills. Doesn't happen. Okay? But what do we see as the general populace? Does the scientist shout out, hey, look at me, I made a crappy pie? Okay? The only thing we ever hear is, hey, look at me, my pie is the best pie on the planet. We don't see any of the work that goes into it. Which is why when students move into science courses, and they start, they're like, well, this dude was amazing. He made an awesome strawberry pie. I'm going to make an awesome kiwi pie. Sorry, we have kiwis at home. Okay? I'm going to make the best kiwi pie. And they could sit down and they try it, and the kiwi pie is awful. They go, well, I must not be a scientist, so I give up. Because I didn't make it like that other person did. The only reason that other person made such an awesome strawberry pie is they hid all of their failures. Right? It's still accessible. We can find that, but we have to look for it. So one of the things that we have to acknowledge when we move into science fields is this isn't an absolute. Okay? There's lots of failure. Okay? And everybody freaks out when I say failure. So one of my colleagues went through and said, well, you have to soften that a little bit. Okay? And he said there's two types of failure. There's lowercase failure. That's good. We learn from lowercase failure. We grow. Okay? We become better. There's also capital F failure. That's the end of it. We give up and we walk away. What I want you to do in this class is fail. Yeah. Lowercase failure. You need to struggle through it, hit those walls and be like, oh my God, I don't know what to do. Okay? What if I try this tactic? Can I talk to this person to get some help to help me move through the class? That's what I want you to do, is hit those failures. And I want you to hit them in very particular points in the class. Okay? I want you to hit those failures in this classroom when I'm talking. Okay? When I ask a question, what is today? Okay? We had two answers. Thursday, August, what did you say? 23rd. Okay? Who's right? Okay? The question was intentionally vague. Okay? It opens up the now thought of, well, should we be specifying more information beyond Thursday? Is it August 23rd, 1995? No, you're wrong. Okay? That's a small failure, but we can now learn from that and grow. Make sense? Okay, roster? Really, everybody? Everybody got it? Okay, cool. Okay, which takes us to the scientific method, which you've probably learned about and you read about. And with the context we've just addressed, you may see some things happening different here. So ultimately, the scientific method is about learning something new. Okay? What we do with that knowledge is now a secondary feature. Okay? In my opinion, we should share that with the world and just move on. Okay? Other people think that we should sell that to the world so that we become more wealthy, or we can get credit for the work that we did. Okay? So, one of those first things is observation. Okay? We could look at it as an apple falling from a tree. That's an observation. Why did that apple fall from that tree? So I would then come up with Okay? A hypothesis.
Apples fall from trees.
Apples fall from trees because there is some force causing that apple to fall from that tree. Okay? What is that force? Well, I don't know. Okay? Asking that question is a good first step, but then what do I have to do? I have to answer it. To answer it, I have to create a question that's arguably the hypothesis, design an experiment. Okay, so I've got an experiment. Wow, that was kind of spooky. You guys are all face up, and then as soon as a word pops up, okay. Remember, the lectures are posted online. The words are there. Okay, so you don't have to be like so vigorous, just pointing it out. Now what happens? Right, we could talk about reviewing results, okay, which I kind of tie in with experiment. We should come up with a conclusion. And what do we call our conclusions from scientific method? Some of you read, right? Theory. I honestly don't remember the words chosen. I gotta look real quickly. Theory, scientific theory, or natural law. Both of those are wrong. Your experiment sucked. Okay? So it failed. You got to go back, readjust your hypothesis, make changes to your experiment. Made it through the experiment, now what happens? You said we had scientific theory and natural. No, your experiment still sucks. Okay, you fail. Okay, remember that whole egomaniacal aspect to this? Okay. 99% of the time, every single scientist out there fails. Okay? They're lowercase failures because what they do is they learn from that, they adjust their hypothesis, they generate a new experiment. That 1% of the time, they actually move forward. Okay? And they get a scientific theory in natural law. And they then publish that and say, look at me, I'm a genius. I created a law. Okay? And this is what I did. I saw something, I made a guess, I did an experiment, and I made the theory. I'm a genius. You as students then come back and look at that and go, oh, that's not that bad. I can just follow those steps. Okay? And then your experiment fails and you go, oh, I'm a bad scientist. No, you're an awesome scientist. Okay? Because it will fail. But you need that kind of egomaniacal drive to say, I'm going to fight through that failure and I'm going to try again. And I'm going to try again. And I'm going to try again. Right? And you might say, isn't that kind of stupid? Isn't that the definition of insanity? I try something, it doesn't work, and I try it again and it still doesn't work, and I keep doing that? That's kind of the definition of insanity. Yes, scientists are egomaniacal, insane people. Okay? What makes them less insane is they make small adjustments. Okay? They take careful notes so that they can reevaluate that process. So when we move through this class, keep that in mind. Failure is good. Find those failures. That's the point of the problem solves. I don't want you to find 20 questions that you know the answers to. That's not going to help you grow. Find 20 questions that you don't know the answers to. See if you can find those answers. Right? If you can't find them, ask for help. If you still can't find them, the due date's done, you can write there, I really couldn't find the answer to this. I'm fine with that. You've put the effort in to try that. I would rather you try 20 times and fail than try 20 times and succeed but learn nothing. Okay? When should you absolutely not fail? Please. The exams. Those are really the crux of the whole class. That's where your grade is determined, is off of those exams. We've provided a bunch of other places in the class to help kind of mitigate some failures in those exams. Right? But if you push all of your kind of failures into the place where failure is okay and you get those points, when you get to the exam, you won't have those failures. Okay? And then your grade looks awesome, and then I look like a great teacher. Okay? Everybody wins. Okay? Make sense? So, chemistry's role in this. Okay? We've got a bunch of different fields up here. We'll just kind of briefly talk about this. And we got a bridge, saying we're connecting two sides of thought. Okay? Depending on who you talk to, biologists, physicists, mathematicians should admit they are not the bridge, but it is possible that every single one of these fields says they bridge. I am the bridge between the theoretical world and the real world. Okay? Everybody says that. Chemists are right. Thank you for a smile. I appreciate that. Okay? Chemists are the bridge. We have the mathematics and the physics. Chemists take that mathematics and that physics, and they spin that, repackage that, and say that explains why this happens. They then give that to the biologists, and the biologists go, oh, cool, I'm not going to look at that. Okay? Why? Because they're busy at looking at a different level. Okay? They don't need to know necessarily all of the whys that chemistry brings in. By that same token, there's a lot of stuff in physics that explains the whys of what we see in chemistry. And what do chemists do? I don't need to see all that. Those numbers scare me. Okay? So we all kind of contribute to general thought moving forward. And depending on our abilities or kind of our level of egotism, right, we would fall at different levels. Mathematicians are probably the most egotistical, right, because they have to deal with a lot of failure with all the numbers. Okay? Oh, I entered into the calculator wrong. Failure. Okay, let's fix that. Okay? Oops, I used the wrong symbol. Failure. Let's fix that. Okay? Physicists have to take, in theory, mathematicians' good stuff and apply that out to the real world. Chemists take the good stuff from the physicists and move forward. Biologists deal with less and less, progressively less failure because those mistakes were made further back in the food chain. Okay? So you get some people saying, well, biology is so much easier. All I have to do is memorize a bunch of facts. Where would those facts come from? Biologists making a bunch of failures. Okay? So depending at where you are, you may have to have a larger ego to move through it. Okay? So that's chapter 1, sort of in a nutshell. If we jump up to chapter 3, we're looking at now matter. We're going to skip chapter 2. And if you're looking at the 7th edition, the PSS thing, it's a bunch of math stuff. We'll talk about that a little bit later. Okay? So, in matter, and we're now looking at that observational state for everything. And there's really two kind of classifications for observation, qualitative and quantitative. Okay? There's a picture there. What kind of qualitative observation could you make? Okay, what is it? That was the wrong button. Let's try that again. Okay, we have a sheep. How many sheep do we have?
2.
Yeah, there's that dude hiding in the back. 2 sheep. Is that qualitative? No, that's quantitative, because now I'm specifying the amount. Okay. What other qualitative observations could I make? Okay. White, gray. Does everybody agree that's either a white or gray sheep? I think it looks more kind of eggshell.
Good observation.
Thank you. I tried on that one. Maybe cream.
Vanilla.
No, that one's getting too far out. Okay. Is there another quantitative observation that we could potentially make?
2 years. 3.
We could start counting the number of ears that we see. What other kind of quantitative observations could be made? And this one gets a little bit harder, because at this point all we're doing is counting stuff. Okay? And those bring in numbers. Is there another thing that we could use to, say, measure?
It weighs about a certain amount.
It's the weight of the
8
sheep.
pounds.
Anybody know the weight of a sheep?
Sheep.
Usually there's someone with some kind of farm experience that can give me a number. Nobody?
70 pounds.
70 pounds? 70 pounds. LBS. What the heck is LBS? No, that's probably pounds, right? Some people shook their head. Why did you shake your head at me? What's wrong? What is LBS?
Pounds.
Oh, it is pounds. So depending on what number may change what I write for the symbol. Why would I write LBS instead of pounds?
It's shorter.
It's shorter. You mean scientists are lazy and don't want to write everything out? Not only are they egomaniacal, they're insanely lazy. Okay? And so we will come up with abbreviations to shorten that. You appreciate that because I'm pretty darn sure you're also lazy. Okay? Because if I made you write out pounds for everything, you'd probably be upset. Okay? Did it have to be pounds?
No,
I would have said sheep might have also been measured in kilograms. Right? God, that's a lot of letters. kg. Right? Which of those sets of observations is more important? Quantitative. Okay. I make sweaters. Do I care about the weight of the sheep?
Yeah. That's your wool that you're using to make the sweater.
So I get 70 pounds of wool?
No, but the bigger the sheep, the more
The
wool
more
you're gonna
wool.
get.
Potentially. What if the sheep had already been shorn?
Then you definitely wanna know about that?
Yeah.
Okay. Is the shorn observation a quantitative or a qualitative?
Qualitative.
Qualitative. Which one's more important?
Neither.
The qualitative now. Okay. I'm a butcher. I care about the quantitative. Okay. The amount of the wool on that sheep probably isn't contributing to the weight all that much. Granted, I don't know a lot about sheep, but I don't think it contributes that much. Okay. I'm more concerned about the weight of the sheep because that is then related to the amount of money I can make after I butcher the sheep. It happens. Oh, you guys laughing at that. Right? So which one's more important? Yeah, there we go. They're both important. Depending on the circumstances or the context in which we look, we may need to evaluate one or the other. This means when we move into lab, we aren't taking just quantitative observations. We have to take qualitative observations. Okay? Those qualitative observations can sometimes cancel the effectiveness of a quantitative observation. Right? One of the things that is a bit unfortunate with pretty much all our labs is we have a heavy emphasis on quantitative. Okay? Some of you probably came into this class of chemistry and were concerned about the mathematics behind it. Is that true? Yeah. So what did you think when you heard chemistry? What was the observation that you were thinking about? You were only concerned about the quantitative observation. Okay? It is important, and we will evaluate it a lot. Okay? But the qualitative can be just as useful, and we can't forget about that. We have to think about that qualitative aspect when we look at our science. Okay? So, qualitative observations tend to be one of the first ones discovered. Why, or used? Why would the qualitative observation be the first observation made? Okay? It's kind of a C. Okay? How do we determine the mass or the weight of our sheep? We had to weigh it. How do I weigh it? I need an instrument to take that measurement. Nearly all of my quantitative observations are things that I require an instrument. The qualitative can be done relatively quickly just by inspection. Right? So qualitative tends to be more common. Right? So let's look at some qualitative observations. 70 to 80% of life as we know it is water. Carbon's not a bad toss-out either. Okay? Water. Why would water be a really important thing for us to observe?
Without it, we die.
Okay? Without it, we'd die. Okay? All of our life is based off of it. It is 70 to 80% of the composition of life. What else is interesting about water? There's a limited supply.
It's solid gas and something else.
If we make qualitative observations within this room, we could make qualitative observations about, say, the people in here. Those are most sort of solid. The desks, the chairs. You made an observation when you came into the room to try and sit down in a chair and not sit down in the air. Why not? You're like, why would you do that? How do you do that? Why is it a how do you do that? What does the air do? The air supports you, so if I tried to sit down right now in the air, you're all going to be like, yep, he's just going to float there.
The air moves.
The air moves. Freely moves away from you. It doesn't have that physical kind of corporeal sense. But the chair does. Okay? Interesting. There's a different system there. Right? One is solid, one is gas. Right? If I just, because I don't have a better example right now, I just started spitting randomly into the air. I know I'm teaching and probably doing that, but if you could actually see it, okay, you'd be a little bit more concerned about that because I'm spitting on you, yeah. What is that phase? A liquid. Does that liquid have different properties than, say, the air? Because I am sort of kind of spitting on you all already just by speaking. Because to speak, what's happening? Air's moving from my lungs and out on you. You aren't really concerned about the air coming out of, well, now you probably are. But if it was a liquid coming out at you, you're probably going to be a little more concerned. Why? Germs. Okay. Does the liquid just completely free move around? No. Its properties are slightly different. It'll probably hit you and, yeah, it's just bad. Okay? If it was a solid that I was breathing out, and you're ducking, okay? So those phases are important to make observations about, and we've already made a lots of observations about these. So we can look at the shape, volumes, and compressibility of each of those, and those are things that you've already kind of experienced in your life, okay? And that's why the textbook addresses those. Because we're trying to look at those differences and come up with those relationships. Kind of make sense? Okay, so let's take a look at matter, because this brings in some fun new terms, and I got 3 minutes. So we look at matter and divide it out into categories. We could go through and look at solid, liquids, and gases. Those are kind of the bulk phases of matter. But we now want to look at separations within matter. Right? We end up with mixtures and pure substances. Right? Remember, this is really early on, right? How many of you have had more than, because officially we started half an hour ago talking about, had more than a half an hour of chemistry lecture before? Okay, 2 or 3 people. It was more than that. I can't count, but that's fine. Not everybody has. Okay? Let's take a look at a pure substance. What is the definition we are using for a pure substance? Chemically linked. We are using the name of the course that you know nothing about to define something. Anybody see any problems with that? If you don't know what chemistry is, how the heck are you going to be able to use chemically linked to explain this? Right? It's defining a word with more words that you don't know. Okay? It's a bit unfortunate, but that's how we've established this. Okay? So we will get into that chemically linked relatively quickly in the semester. Our mixture is spatially linked. Okay? So the analogy we could use here, we're all spatially linked. We would be a mixture. Okay? A pure substance is chemically linked. My arm is chemically linked to my body. Okay? If my arm and my body were a mixture and they were just spatially linked, that means my arm would just kind of fall off. Right? Which would be kind of spooky. Right? In my opinion, at least. Okay? When we look at each of those substances, we can further subcategorize those. Our mixtures come in as either heterogeneous or homogeneous. Okay? Are heterogeneous. There's a visible separation. Okay? The other way to think about heterogeneous, because we know solids, liquids, and gases, heterogeneous is multiple phases. Homogeneous, there's no visible separation because they're all in the same phase. They're either all solid, same solid, all liquid, same liquid, or all gas, same gas. For pure substances, we're looking at compounds. Okay? So we started with a word we didn't really know, used a definition of another word that we didn't really know, to then move to yet another word that we don't really know, added with a definition of more words, we don't really know. Awesome. Way to go, science. What are elements? Yes, good eyes. Periodic table of elements. Okay? If I take multiple elements and I combine them together with a chemical linkage, I now have a compound. Okay? If I take elements and just have that single element on its own, I'm looking at just the element. Okay? Those can be categorized as pure substances. If I now take mixtures and spatially link them, that's where I move into heterogeneous and homogeneous, which we'll have to pick up with there Tuesday.